Morning, everyone. So to finish off our review here, I want to just highlight through some of the main things that we learned from our circuit section. First thing that we want to do here is there's two types of circuits that we can investigate. One is referred to as a DC circuit, which is a direct current circuit. This is the one that we dealt with. And basically this means the electrons can only flow in one direction. Most of our electrical devices, we just plug into a wall socket. Our wall socket actually gives us what's referred to as alternating current. It just has to do with how we actually create that current here. It's basically like a magnet that's sort of rocked back and forth. It has a certain frequency. Most of our frequencies in our walls are about 60 hertz or so. This one here is it sort of constantly changes back and forth between two directions. So just for simplicity for us this year, we're just focusing on direct current. We're just focusing on electron flow. We started drawing what are called circuit diagrams. For a circuit diagram, yes, although realistically your wiring may be curled and sort of overlapped and twisted together, for a circuit diagram we try to keep things all nice and 90 degrees so it's really easy to read. For a typical DC circuit, we need at least 3 components. Usually we say 4. First component here is called source. We're going to use this symbol here, long line, short line. I think of this one here as a battery, like a AA battery. The positive end is a side that protrudes out. The other side is the negative on the other side here. So long line is the positive, negatives on this side here. This is the source. This one here as our battery. You can say our battery provides the voltage. There is another name for voltage that's called potential, but be very careful. Potential is different from potential energy. So this one here is like a parking lot. All the cars are sitting in here. The battery here provides the cars a little bit of a push to actually go through the rest of the circuit. Again, as I mentioned, we're going to try to keep our lines as 90 degrees as possible. So we have, that's our second component here. Our second component is referred to as a conductor. Usually it's going to be just wiring made out of metal. So this could be a metal wire. And we use metals because metals are conductive. Metal wire for its conductivity. For conductivity in general, we need to have charges and we need to have the ability to move. Metals have what are called metallic bonding here, so charges can move through them no problem. Now, I never want to basically hook up a battery like that. You're gonna have pretty much no resistance through the wiring itself. Basically, there's going to be a lot of voltage just pushing the charges along here. That's going to at risk of like overheating the battery and cause a fire hazard. What you always want to make sure is you have a load. Load is a fancy term here. The word load basically is a resistor. This one here is essentially the device that we're trying to run. So it could be, for example, we have a bulb that's converting the electrical energy that the charges had, converting it back to light energy. It could be something like a buzzer. A buzzer converts the electrical energy back into sound energy. Yes, definitely every time we do an energy transformation, we're always fighting a losing battle. We always have a sort of not 100% efficient circuit, so we always lose some in the process, but our hope is we still have enough left over to run whatever devices that I wanted. That's technically all you need in a circuit, but just to be environmentally friendly here, I don't want to actually let this circuit just run on end. That's going to burn through the battery really quickly, might even risk it burning out my light bulb. So what we're going to do is we're going to throw on a switch. It really doesn't matter where your switch is. So let me just put the switch here, let's say on the bottom here. The switch here acts like a door. Right now the switch, when it's connecting the circuit, I can say the switch is in the closed position, and for a closed position your circuit here is on, the light bulb is on, the buzzer is beeping, and in this case here, if I open the door, the switch is therefore in the open position, and in the open position that's like you have turned off the light. You've effectively broken the circuit, and whenever you need to turn on this device again, you just close the circuit. We need to have one complete path or charges are not going to flow. Now, this is sort of just an unfortunate thing left over from history. We had thought it was actually positive charges that actually move. So we had thought we had, you can call them positrons here, basically the antiparticle of an electron. This does actually exist, but we had thought it was actually these positive particles. If I'm positive, we know like charges repel away from each other, positive charges want to go away from the positive end and go from positive to negative. All of our formulas have been dealing with that here. We're going to just give that a new name here. We're going to call that the conventional current. So conventional current here assumes we have positive charges flowing from the positive terminal of the battery to the negative terminal of the battery. What's actually happening? Well, actually, it's not positrons that are moving, it's actually electrons that are moving. And electrons actually have a negative charge. The real electron flow, if I'm a negative particle, I'm actually going to go the opposite way. I'm going to want to run away from the negative terminal, and I want to get to the positive terminal. So we're just going to give that a different name. What's really happening here, you can call that an electron flow. Electrons actually flow in the direction. It's actually negative charges flowing from the negative side to the positive side. Right? But now, instead of redefining all our formulas and everything, just tweaking that here, well, I can just give it a different name. When I do Ohm's law later on, so let's say Ohm's law here, we use this formula quite a lot. Really simple formula, V is equal to IR. The trick was you had to figure out which component I was using Ohm's law on. Basically, conventional current is this I here. So let me just list off some of these terms here. Usually this V here is the voltage or the potential from the battery. That's measured in volts. The I here is this conventional current, or just current for short. It imagines these positive particles are actually traveling in the opposite direction. That's going to be measured in amperes. And then R is going to be a resistance. R is going to be your load. It's going to slow down. It's going to convert the electric energy into the forms that we want. Our resistor actually provides some ohms of resistance here. Right? To be like really precise here, let me just zoom in back at this battery. So we have our battery. Even though we're going to imagine we have these positive charges that flow from the top end to the bottom end here, because the charges actually need to flow through the battery itself, we usually track here, there's a small resistor inside the battery itself as compared to what true amount of voltage I was supposed to get. So what we do is maybe we have a voltmeter, we set up our two leads here, I connect one side, I connect the other side here, and I actually call that the terminal voltage, the voltage between the terminals on the battery. The terminal voltage is actually the true EMF. It's the true voltage that your reactions are supposed to give you. If you go on to Chemistry 12, we're going to actually analyze the anode and the cathode and figure out which reactions actually allow for this electron transfer. But for us, we're just going to have, well, it needed to travel through the bulkiness of this battery. There's usually a tiny little R. If I worry about how much voltage I lost there, we're going to have lost a little bit of voltage, I times R, and this R here is called an internal resistance. So the overall voltage that I have access, that's free for me to use, is actually a little bit less, not by much, but a little bit less than the true voltage that I could have gotten. I can call this the true, they call it an EMF, which is the electromotive force. This is the true voltage supplied by your reactions, our extended reactions, right? So just be careful. Usually we ignore that. Usually we just say, oh, here's the terminal voltage of the battery. Every now and then I might ask you for calculating the true EMF. Right? Let me just show you the two main setups, and then we'll just practice through a problem or two. These circuits here can be in series, or they can be what's called parallel. In series, not only are we dealing with direct current, where they can only flow in one direction. In this case here, we really only have one path from start to finish. So if I put my batteries here, technically speaking, every single long line, short line can be called a electrochemical cell. That's what's actually generating the voltage. A battery is usually a couple of these cells here hooked up in series. And basically for a series circuit, I only have one way around the circuit. I have the positive end and the negative end here. Any current that comes out of the battery, any cars that come out of the battery, they only really have one path to go. They have to run through this resistor no matter what they do. This is in contrast with a parallel circuit. For a parallel circuit, we actually have multiple paths. Many paths, we have branches, we have junctions. Those are some words that we like throwing in here. We have branches, or we have junctions. We have turning off points where they can actually go down whichever path that they want. And essentially what that looks like here is we have our battery again. Our circuit diagram would have a long line, short line. And then basically instead of just having a single path, we actually have more paths. Could be any number of paths. And we can have combination circuits here. In our problems, we're going to deal with what's part series and part parallel. There's even some circuits that are neither series nor parallel. That's totally possible. You can think about how you design that here. In general, though, you can say for a parallel circuit, because there's more pathways, even if these pathways here are really hard individually, having more paths is actually easier to get around. As we step through some questions here, we talked about two different devices. First device here, we called it an ammeter. An ammeter here measures current. And what I want you to note for an ammeter is an ammeter has to be hooked up in series. Because it measures the current, you just basically plop this ammeter along the path that you're interested in, and as the current flows through it, the ammeter will just sense how quickly the charges are passing. For a voltmeter, however, a voltmeter, we actually hook it up in parallel. Basically, a voltmeter has a lot of resistance. I don't want a lot of electrons to flow through here because I want all the electrons that used to flow through resistor number 3 here would basically still go through. I'm just sampling the potential difference, the potential drop across. So for a voltmeter here, as the name suggests, it measures the voltage, measures the potential difference, and this one here has to be hooked up in parallel. So I'm just going to remind you of Kirchhoffs' two laws, and then we're ready just to practice a circuit or two. Basically, for this DC circuit stuff here, Kirchhoff had two laws for us here. First law was the fact, it was called the loop rule. And basically that says, around any closed loop, the sum of the voltages around a loop must equal to 0. Any gains that I had, by the time I get back to that spot here, I have to have lost all the voltage. Second one here, we're going to call it junction rule. Essentially, the charges have to go somewhere, especially as I enter into a junction, a turning off point. The number of cars coming into a junction, they get split off between the different pathways available. But what we're going to have is the sum of the current into a junction has to equal the part that's leaving the junction. Okay. So as we work through a problem or two here, we're going to see these laws being applied. Not a very big section. Hopefully it should have been pretty easy as well, but let's just work through a quick question. So just as an example here, let's start off with a 9-volt battery. Now, yes, a 9-volt battery actually has the positive and the negative terminal here on the same side, but that doesn't matter. On a circuit diagram, we still have one side positive, negative. Let's say at first I design a parallel path. First pathway here, let's say it's a 5 ohm resistor. The other pathway that we get through here, I'm told it's a 3 ohm resistor, and I'm actually told the current going down this path here is 2 amps. Right. So that's the setup there. That part there is definitely parallel. We're going to force it to go through one more resistor, but this one, this resistor here is in series. What we're going to do here, I want you to calculate a couple things here. So I want you to calculate, let's call this sort of path 1 and path 2. So I want you to find I2, so that's this path going this way. Find the I2, find R1. So R1 is going to be the first resistor, R1. And seemingly we don't have enough information for this bottom piece here. Let's call this resistor number 3. Let's see if we can work through our math there. Can you find for me, maybe as a second step, let's say that's part A. Part B, I want you to calculate the current going through there. You can call it a total current, I3 if you like. I3, what's the total resistance for that circuit, and what is the voltage for that circuit there. Right. And I encourage you just to pause the video and see how we do. You can check your work with me. So let's start off with the loop rule. Basically what it says here is, if I imagine this to be a water slide, all the electrons start, or all the charges, positrons here start out on the bottom of the slide here. The 9 volts are a staircase. They give me some energy to flow through the rest of the slide. As I go around the loop, I could either take the first path, go down R1 and then go down R3 and back. I have to have used all my voltage, or I can use the other path and likewise have used all my voltage. I gain 9 volts by getting up to the top of the slide. By the end of it, I had to have lost all that voltage. Let's start off with where we know most information. So I actually know most just in this second path here. even though this path here makes it look like this path here, it's a little bit of detour, it's a little bit longer, there's more wiring necessary, there actually is no preference there. Remember, all the charges are already lined up anyways. All that's really happening is one person is pushing the next to them, pushing the next to them. They're just pushing the person in front of them. The signal passes quickly, so it doesn't really matter that it looks like there's a different distance here. We're going to use Ohm's law, which is a very simple rule here, but just be careful when you use Ohm's law, which part are you looking at? So let's actually do Ohm's law right here. So V is equal to IR. I have the current, which is 2 amps, and I know that the resistor here is 3. My Ohm's law would say I'm actually using up 6 volts here. Right? So that case there, I figured out 6 volts. I found the voltage to here. Because these two resistors are in parallel, if I use up 6 volts over here, I would also need to have used up 6 volts for the first resistor. If you want to loop rule here, this one here, the loop rule actually would work down here. I had lost 6 going through this one. If I went back up through the resistor, I would need to gain 6 so that I actually end up back at 0. That's an application of the loop rule there. Right? But now that for resistor number 1, I now know the voltage and the resistance, I can do Ohm's law at this part. So V is equal to IR. We have the voltage of 6. The current I don't know, I'll call it I1. The R happens to be 5. So the current here is actually going to be 6 divided by 5, so 1.2 amperes. Right? So I found the I2, and we found the, did I find the R1? Oh, sorry, the R1 is actually given to you. Okay, so let's just keep going here. Now we'll do the junction rule here. Well, I now know I have 1.2 cars coming down this way. I now know I have 2 amps going this way here. In total, all the current coming into the junction has to be all the current going out of the junction. So in this case here, this will end up giving you 3.2 amps. So simply, what's the total current here? I total. It's 1.2 plus 2 amps. So therefore, I'm going to end up getting 3.2 amps. And now that I have the current here, I do need the loop rule one more time here. I had gained 9 volts. Through either of these resistors here, I'm actually losing 6 volts at a time. How much voltage do I have left over just for this bottom circuit? Well, 9 volts, I lost 6, I still have 3 volts left. I still have 3 volts left here. And in this case, anytime you have 2 of the 3 variables, we can do our Ohm's law. V is equal to IR. We have 3 volts to be lost, a potential difference left over. The total current is 3.2, and there we can find the R total just in that last resistor, 3 divided by 3.2. Gives you the R of 0.94 amps, ohms. Right? So it's sort of like a puzzle. You sort of work your way through. Let me give you one just to practice, and then we'll deal with the power question together here. This one I'm going to leave it for you to solve out. Let's imagine this time I have my battery, it's 6 volts. This time I have 3 parallel paths. Right. And then it runs into 2 parallel paths. Right. This can be horrendous here. What I'm going to give you in this question here is I'm going to give you all the resistances. So 1 ohm, 2 ohm, 3 ohm, 4 ohm, 5 ohm, just to keep things really simple. I want you to calculate for me here, A, find the equivalent resistance. So let me just hint at how you're going to do that here. Basically, I know this parallel combination is really complicated. I can't use Ohm's law just yet because the current actually gets divvied down 3 different pathways. If I want to swap out these 3 resistors for a single resistor, what size would that resistor need to be? Remember, for parallel, we go 1 over R parallel is 1 over 1 over R1 plus 1 over R2 plus 1 over R3. We can do exactly the same on the bottom here. So for these guys here, 1 over, again, these two are in parallel as well, 1 over R4 plus 1 over R5. That would basically replace these parallel combinations, the 3 pathways, the 2 pathways there. Then I would have 2 resistors in series, and then for series, we can combine these two here. The total resistance in series is basically R from the first one plus R from the second one. So see if you can find that total resistance. You're going to basically have simplified the circuit enough into a really basic circuit. Then we're going to have a 6 volt. We have 1 resistor with that equivalent resistance that you just calculate in part A. Then you can calculate for me, well, how much current is actually going to flow out of this battery to actually get out of this battery here, given that's your resistance ahead. Current technically is a charge over time. It's technically measuring a speed. We've just been using an analogy of how many cars just for simplicity. Right, so you can find that current there. Once you know the current in the equivalent circuit, that is the current in the first step as well. And then you can backtrack here. If I know how much voltage I'm being lost through each of these resistors here, you can then find what the individual voltage is, what the individual currents are going down this path. Okay, so I'll leave that for you to try here. Find the equivalent resistance, calculate the total current, and find the potential difference, the potential drop across the parallel paths. So I know regardless of which path that I take, I'm going to lose some voltage here, some of my 6 volts. I know regardless of which path I take on the bottom, I'm going to lose another part here. What is the voltage that I lose in between there? Right. One last question here. Now that we have these circuit components here, there's a couple last formulas. We can actually figure out the power of a light bulb. Power actually amounts to, this is the same work over time like we saw in the energy section. Power amounts in this section here as the brightness of the bulb. And basically, if you know the current, if you know how fast the charges are actually moving by, and you actually know the voltage, how much of that push from the battery am I going to use up just for this light bulb, by multiplying those two, we can actually just calculate the brightness, I times V. Because we have V is equal to IR, right? So I'm going to use Ohm's law. V is equal to IR. I can actually write this in a couple of different ways. Power is also equal to I squared R is also equal to V squared over R. Right? So depending on which variables that you have, any of these formulas end up working out. Again, I'll let you solve your way through for this problem here. We're going to start off with a battery. This battery here, let's say it's a 70-volt battery, right? Huge battery. I'm going to hook up, again, one resistor in series and then one path that's in parallel. Hopefully you played around enough with the virtual simulation so you know how to build this circuit pretty easily. I'm going to give you a few of these numbers here. I'm going to tell you that there's actually 5 amps that actually come out of the total battery. The first resistor here is 8 ohms. I'm going to have a 7 ohm path. I'm going to have a 9 ohm path. What I want you to find for me here, well, what's the voltage drop across, let's call it V1. What's the voltage drop across these ones as well? So what's V2? What's V3 here? You would need to be careful of the junction rule here. I have 5 amps coming down this way. Let's say 3 amps heads down this path. I'm going to help you out a little bit. I want you to actually calculate calculate the power on all 3 light bulbs. Because I have a bunch of voltages and resistances, I might consider doing V squared over R. Or if you know the I, you can just go I times V. It should give you the same number anyways. So you're going to have P1, the brightness of the first bulb, P2, P3, the brightness of each of those bulbs there. And then what I'm going to do is I'm going to say, what if, in part B, what if bulb 3 burns out? Right. If bulb 3 burns out, it basically cuts off this path. Now I've lost that other potential detour here. The overall current is actually going to be a little bit less than 5. And then I want you to track here, if bulb 3 burns out, I want you to do a recalculate here. Find, again, the total current. It's going to be less than 5 amps. The total speed that these cars have traveling through it will be less because one path has sort of totally cut out. Now no longer current can't flow through this path. Now we only have one series path left over. Find out the total current and then calculate P1 and P2 again. Compare, are we brighter? Did the light bulbs, the other light bulbs that didn't burn out, are they now brighter or are they now dimmer than before? Okay. If we know any of these powers here, you can actually calculate the energy as well, because power tells you how much energy you lose over time. You can actually rearrange that. The amount of energy is based on your power rating times how long you spend for it. So if you actually know these powers here, let's say I run the circuit here for 5 minutes. If bulbs are lit for 5 minutes, you would need to convert that to seconds, so times 60. 5 minutes times 60 is 300 seconds, you can just take the individual powers that you have, take that power times it by 300, and that'll actually tell you your energy consumption. This energy consumption will be given in joules. Okay, so I just left you with 2 circuits there. Play around with it a little bit here. Keep working your way through the worksheet, and let me know if you have any questions. Thanks, guys.